Hi, I'm Alexander Holroyd and this is the Outomorph. So as you can see we have 6 coloured pieces, and at the moment it's in the solved state because the pieces match the colour at the side with the white one in the middle. But I can scramble it by rotating this square and rotating this square. And now you can see it's somewhat scrambled because some of the pieces do not match, and it turns out it's possible to get to all possible permutations or arrangement of the 6 coloured squares, so that's 6 factorial or 720 possible states, but nevertheless it's not a very difficult puzzle to unscramble it. However, if I turn it over, then I actually have an identical copy of the puzzle on the back. But the two of them are linked because when I rotate this square, the black pieces are actually the coloured pieces on the other side, and vice versa. So the two sides are linked, and you might think that would make it a much more difficult puzzle to solve both of them simultaneously. But it turns out if I solve one side, like this, so, okay, now this side is solved, then miraculously the other side is solved as well. And it turns out that will always be the case. If I solve one side, then the other side is automatically solved. So that actually means that there is a one-to-one correspondence between the states, the 6 factorial permutations on one side, and the possible states on the other side. In mathematical terminology, that's called an automorphism of the group of states. It's called the symmetric group on 6 elements. So what is this correspondence? What is it like? So you might think it's somehow just corresponds to a rearrangement of the pieces or a relabeling of the colours or something like that. But and if that were the case, it would be called an inner automorphism. But actually that's not the case. So I can demonstrate that by, if I do this sequence of moves, for example. Okay, so now it's not in the solved state, but there are only 2 pieces swapped. These two, everything else is in its home position. And now if I turn it over, you would expect that there must be 2 pieces swapped on the other side, but actually that's not the case. Every piece is in the wrong position, and actually there are 3 pairs swapped, green and white, and this pair and this pair. So the correspondence between the 2 sides is something much more subtle that can't arise just as a relabeling or a rearrangement of the pieces, and in mathematical terms it's called an outer automorphism of the symmetric group on 6 elements. And it turns out this is a very important mathematical object, and it turns out it is there's essentially only one correspondence like this, and it's only possible for the symmetric group with 6 elements, no more, no less. So it's a very remarkable mathematical object, and so far as I know, this is the first implementation of it in physical form. Thank you for watching.